Hi everyone, this is our project, Frequency Aware Multitask Learning for Generalizable Deepfake Detection, and this is Milestone 2 presented by Amal and Nadia. The core problem we are trying to solve is generalization gap. Deepfake detectors hit over 99% EUC on clean benchmark data, but the moment you add real world video compression, the performance collapses. ECCE, which is our model, drops from 97 on clean C23 C23 to 74 and heavily compressed C40 videos. So what we are trying to do is to try to reduce this gap between both. Moving to our data set, we use two main data set, Face Forensics Plus Plus, which gives us 1,000 real and 4,000 fake videos across four manipulation method tested at both C23 and C40, while deep fake will be used in the last milestone to see the generalization.
So moving on to the survey of the existing methods, we surveyed 5 models family. You can see that the Face Forensics Plus Plus performance is high across the board, but cross data you see such as in CDF and the DFDC and wild DF varies drastically. RISI holds the best wild DF score at 64%, which is why this is our starting point. And now moving on to why we choose RISI as our baseline. So RISI, so as you can see here, that RISI performs the best across the board, so that's why we're going to keep it, and it has the pre-trained weights and the code publicly available. The RISI architecture looks as follows. It uses the reconstruction paradigm. It learns what a real face looks like, then flags the images it fails to reconstruct cleanly. The pipeline is an exception encoder, reconstruction decoder, graph reasoning to fuse multi-scale features, and a guided attention using reconstruction error to highlight the manipulated regions. And
Okay, our plan had three pillars: a frequency branch using FFT to catch GAN fingerprint invisible in the pixel space; CBAM attention to focus on the manipulation-prone regions like eye and mouth boundaries; and a multitask head that adds manipulation type and segmentation supervision during training. Only binary classification at inference. In milestone 1, we added the frequency branch and improved training with augmentation, more frames, and higher dropout. This
now moving on to our milestone 2 changes. So in milestone 2, we tested 5 configurations, and these 5 configurations were based on the implementation of CBAM and multi-head attention, in addition to using the frequency-based data augmentation that performed the best last time. We ran multiple combinations of each, and we tried to optimize each on its own and then combine them together to find the best configuration. And similar to what Amal has mentioned, we trained on C23 light compression, and then we tested on C40 heavy compression, which is the same protocol. And again, our goal is to identify which attention combination generalizes under the real world compression.
In milestone 2, we tested 5 configuration. The key results is run 5, combining CBAM frequency augmentation and the multitask ahead which hits 81.6 accuracy on C40 while holding 97 on C23. That cuts the generalization gap from 0.23 down to 0.154, a 33% reduction. Importantly, CBAM alone in run 2 gave us a big jump to 80.48 accuracy, confirming that spatial attention is a strong standalone contributor. Adding frequency on the top of CBAM actually hurt slightly in run 3, but bringing in the multitask head recovered everything and pushed higher. The bar chart and the line curve. Can we move to the bar chart to show that? The bar chart and the line curve on the next slide make the progression clear, as we can see here, the difference between gaps.
And moving on to the confusion matrices, this is the C23 confusion matrices, and these confirm the results that you saw on the table before. This is simply running our changes. Our changes on the training data and seeing the AUC score. That is why the accuracy is very high, as you can see. Moving on to the C40 confusion matrices, the C40 confusion matrices, of course, have a bit of lower results. However, they clearly see that we are able to close the generalization gap by combining both the frequency CBAM and the attention, by looking at the numbers of videos that were predicted correctly. Moving on to the learned outcomes, so the first thing that we learned is that frequency-based augmentation actually taught the model to manipulate artifacts beyond the pixel level, and this improves the generalization across compression levels, which was a major issue in previous models. Then in addition to that, we introduced a single level CBAM, and this single level CBAM, while it did not produce the best results, it confirmed that explicitly guiding spatial and channel-wise attention recovered the forgery signals that augmentation left underutilized. However, a single CBAM block can only capture forgery signals at one level of abstraction, missing the progressive refinement needed to adjust both coarse and regional manipulations and subtle boundaries artifacts simultaneously. That's why we started to stack the CBAM, and finally we learned that data augmentation, CBAM, and multi-head are complementary. Augmentation diversifies what the model learns, so beyond the pixel level, and at the same time attention sharpens how we apply that knowledge, whether it's CBAM or multi-head attention. Moving on to the next steps in the timeline, so we will be training the model one last time on the deepfake dataset to prove our hypothesis or confirm our hypothesis, and then we're going to generate all the required figures, write the final report, and finally create a website and a demo to see what the classification looks like. And this is the team contribution distributed between us, and that's it. Thank you for your time.